Arham is a high school student in grade 12 at Wilfrid Laurier School, London, Ontario, in Canada. Arham is talking about his AI work on Alzheimer's disease. Arham, go ahead.
Hi, my name is Arham. I'm in grade 12 and I work on novel Alzheimer's diagnostics. My project formulates an early Alzheimer's disease diagnostic via three aims. First, to empirically derive a network of brain regions affected in preclinical Alzheimer's disease-related patterns of olfactory disorder through a systematic literature search. Second, to detect these brain regions on PET images to develop and validate a deep learning algorithm that can spot the warning signs of Alzheimer's disease well before we are aware of them. And last, to design an olfactory test that uses these affected brain regions to diagnose preclinical Alzheimer's disease as an alternative to expensive and time-consuming imaging. Now, what are the problems with diagnosing Alzheimer's disease? Well, there are two. Despite a wealth of information concerning AD pathophysiology, it still remains unclear. And second, current techniques diagnose AD loosely and at a stage where it becomes too late to initiate disease-modifying treatments. Now, why olfactory brain regions? Because patients with Alzheimer's disease experience deficits in the four basic electroolfactogram or EOG modalities of the olfactory mechanism a lot earlier and stronger than other disorders with olfactory problems. Number one, in the rate coding and phase coding in odor perception and detection. Two, in odor discrimination. Three, in odor hedonics. And four, odor habituation. Now, in our brains, smell sensation depends on a distributed network. However, which of these brain regions and networks are affected in preclinical Alzheimer's disease remains unclear. This brings me to the first aim of my project. Through a systematic literature search and deep learning findings, I derived a network of brain regions consisting of 34 locations by mapping them onto an MNI sixth generation brain atlas, and then overlapping it to a functional connectivity AD neurosynth database from 1,000 healthy participants by applying the Fisher-Z transformation and then calculating a T-map for each location. Next, the regions of interest were identified by a clustering algorithm containing at least 250 millimeter cubed and one fully connected voxel. Here you can see the intersection of positive connectivity and negative connectivity, positive connectivity in the blue and the negative connectivity in the, positive connectivity in the red and the negative connectivity in the blue. With my identified network, highlights a specific network of 6 areas, which are in purple, that are highly likely to be affected in preclinical Alzheimer's disease. Now, finally, based on the sensitivity and specificity analysis and bar height above each region, my systematic literature search identified 5 locations as independent predictors of preclinical Alzheimer's disease, including the anterior olfactory nucleus, the posterior and anterior piriform cortex, the anterior cortical nucleus of the amygdala, the rostral entorhinal cortex, and orbofrontal cortex. Now, these brain regions can be used to detect preclinical Alzheimer's disease well before we are aware of it. Now, based on my systematic literature search and deep learning findings, I propose a novel hypothesis of AD pathophysiology that in the preclinical stages of Alzheimer's disease, hypometabolism or energy balance leads to vascular phenotype or reduced brain perfusion or cerebral blood flow, which then leads to an impaired clearance of neurotoxic molecules such as A beta peptide and tangles, which then lead to the deposition of those neurotoxic molecules within the olfactory bulbs. And that leads to a gradual decline or deficit in the olfactory sensory neurons within the orbofrontal, piriform, and entorhinal cortical brain regions. From there, it then spreads to the perihippocampal gyrus, and the posterior parietal cortex in prodromal Alzheimer's disease, and then to the prefrontal cortex, the amygdala, thalamic nuclei, and occipital cortex in early Alzheimer's disease when the patients start complaining about the loss in episodic memory. However, diagnosis at this stage becomes too late to treat Alzheimer's disease. I therefore hypothesize that Alzheimer's disease patterns of olfactory deficit have much higher, earlier, and higher and earlier specificity than episodic memory loss to diagnose Alzheimer's disease in the preclinical stage. This brings me to the second aim of my project. Here, I propose for the first time to apply machine learning technology to test whether my Alzheimer's disease sleep-brain network derived from clinically evident cases of Alzheimer's disease could predict Alzheimer's disease in the preclinical stages using functional PET scans. Here, I use the 89.1 database for data acquisition from PET images to do a retrospective analysis of prospectively collected 1,000 PET images from 450 patients, where 90% of the imaging was then used for model training, while the remaining 10% was used for model testing, serving as the internal test set in the perspective of the algorithm. This table contains the demographics of the datasets that I use. The images are then preprocessed on a 4x4 grid method in Python. An Otsu threshold was then used to sample the image to 2mm isotropic voxels and then cropped to a 200 by 200 by 180 millimeter cubed volume. And then I used connected component analysis or region extraction to use the relevant imaging volume by selecting brain sections with orbital frontal, posterior piriform, and rostral entorhinal cortices. These Brodmann area coordinates, representing around 100 by 100 millimeter squared of brain parenchyma, is then divided into 16 evenly spaced squares with the rostral section in the top left and the caudal section in the bottom right. Here is my deep learning model. After preprocessing the 512 by 512 matrix size images, they are then loaded onto Linux. Inception V3 convolutional neural network that stacks up to 11 inception modules is then fine-tuned using 90% of the ADNI dataset over here, and then tested using the remaining 10%. The input of the model is the 2D images produced in the preprocessing step. To gain further intuition on how my network derives its decisions, here is one average saliency map taken across 10% of the 89 dataset, presented with the anatomy overlay of a 76-year-old woman, to illustrate the connection between the saliency map and anatomy overlay to classify Alzheimer's disease. As you can see, the first and second rows or columns in the first row demonstrate the most intense signal, as such giving them their importance in diagnosing a person with Alzheimer's disease. As you can see, after dimension reduction with TSNE, the features extracted by the Inception V3 network separated 10% of the 89 dataset into 3 clusters. It shows a high sensitivity rate in the 80 class because nearly all patients with Alzheimer's disease are located in this Alzheimer's disease cluster of red dots. Now, the area under this ROC curve shows 100% sensitivity, 92% specificity, 76% precision, and can diagnose Alzheimer's disease 68 months or 5.6 years prior to the final diagnosis compared to a radiologist's performance. These results are in line with my hypothesis that dysfunctioning within the orbital frontal, posterior piriform, and rostral entorhinal cortices is predictive of Alzheimer's disease. And here you can see how my model did compared to a radiologist. Now, this brings me to the last aim of my project. Based on my systematic literature and deep learning findings, I devised a non-semantic test for olfactory sensitivity and olfactory resolution that exclusively engages the orbital frontal, posterior piriform, the rostral entorhinal brain regions. Odor S measures the ability to detect increasing dilutions of a mixture of odorants. Odor R is measures the ability of subjects to discriminate the smell of 2 mixtures that become progressively more similar as the test proceeds. This test tackles all 4 basic elements of cognitive map-based odor deficit that I mentioned earlier. My smell test data should perfectly capture preclinical Alzheimer's pathophysiology as reported in cognition literature. For example, subjects with early olfactory bulb amyloid burden would show poorly affected odor discrimination, hedonics, and habituations with increasing odor complexity and time compared to healthy controls. Now, finally, my conclusion is that this study is the first to institute a novel diagnostic strategy based on spatial olfactory problems in Alzheimer's disease. Second, to empirically derive a network of brain regions affected in preclinical Alzheimer's disease related patterns of olfactory deficits, and to establish the role of the orbital frontal posterior piriform and rostral entorhinal brain regions as novel pharmacologic targets for Alzheimer's disease, and to highlight the strength of my deep learning algorithm that can spot the warning signs of Alzheimer's disease well before aware of them, and it considers the brain as a pixel by pixel volume in its classification, and can also diagnose Alzheimer's disease 68 months or 5.6 years prior to a radiologist. And lastly, to devise a novel olfactory diagnostic test as an alternative to expensive and time-consuming imaging in the future. Thank you for listening.